9.2. We've talked about how to add two vectors together. What we haven't talked about yet is how to multiply two vectors. It turns out there are two different ways we multiply vectors. One is called the dot product, which we're going to talk about in section 9.2, and one is called the cross product, which you'll talk about in Calc 3 when you take Calc 3. We're not going to cover cross product in this class. All right, so some definitions. The dot product. If I take two vectors and I do u dot v, u dot v is defined to be u1 v1 plus u2 v2. What are u1 and v1 and u2 and v2? Correct. Remember, one of our ways for writing vectors, we might write vector u as x and y, u1, u2, or we might write it using i's and j's, and then vector v, we might write it as v1 and v2, like so. Go ahead. Well, to write vector u is going to have u coordinates, x and y, and vector v is going to have x and y. So I write it as v1 and v2 for the x and the y. So, one of the ways to multiply two vectors is kind of weird, because I start with two vectors, and then I multiply. These things here are numbers. u1 and v1 are numbers, u1 and v2 are numbers. So when I multiply numbers, I get a number. So that's kind of a weird way to multiply. When I multiply two vectors, I end up with a regular old number. I don't get a vector. That's called the dot product. The cross product, and again, we don't cover cross product in this course, but cross product is a different way to multiply two vectors, and when you multiply two vectors, you get a different vector. So that's why there's two different ways to multiply vectors. Depends on what you want. Now, the dot product is used for several things. The first off is, this is a theorem, and this theorem is proved in the book. I'm not going to bother proving it. I'm just going to give it to you, and I expect you to know it. This actually uses the law of cosines to prove it. If you take u dot v, the answer you get is the magnitude of u times the magnitude of v times cosine of theta. What's theta? It's the angle between the two vectors. So if you have a vector like this, which is vector u, and you have a vector like this, which is vector v, this angle theta is called the angle between the two vectors. So dot product, using the dot product, is a way to figure out the angle between two vectors. Yes, notice it's a side angle side, which was a law of cosines problem. And so this formula here comes from the law of cosines. Yes. Okay. Next formula we have. This is read the component of vector v in the direction of u. So that's how you read that. The component of vector v, I'm sorry, no, I read it the wrong way. The component of vector u in the direction of v. And that's defined to be the norm of u times cosine theta, or you could write it as u dot v divided by v. In the picture, if this is vector u, and this is vector v, this component of u in the direction of v would be, you kind of think of making a right triangle here. Green. It would be this length right here. So this symbol stands for how long is vector u in the direction of vector v. So you make yourself a little right triangle.
So if they were to come flat, how long?
Correct. So if v and u were in exactly the same direction, if this were u and this were v, then this component, the component of u in the direction of v, would just be the length of v. Correct. Absolutely, you could do it the opposite way. So you could do component of v in the direction of u. That would just be norm of v cosine theta. Nothing in the formula will change other than the position of u's and v's in your formulas. Correct. The projection, this is red projection, the projection of vector u in the direction of vector v is this little vector right here. So it gives you not only the length of that vector, which is the component, it also gives you the direction. So that's the difference between component and projection. Component is the length of the vector. Projection is the actual vector itself. In other words, component is the magnitude of the projection vector. Yes, projection is actually a vector, so projection gives you the component and the direction. It gives you an actual vector because you're multiplying by a vector v here in the end. Okay. All right, so what you're going to need to know here is you're just going to need to know how to figure this stuff out. So I give you two vectors. Consider the vector u is 3, -1, and the vector v is the vector 1, 2. Compute u dot v. All right, well, u, well, we'll see both of these at the same time, I think. But I need more space. I didn't leave enough space in the piece of paper here. All right, so u dot v. According to the definition, u dot v, you multiply the x numbers together. So you take 3 times 1 plus, and then you multiply the y numbers together. -1 times 2. That looks like 3 minus 2. That looks like 1. So u dot v would be the number 1. I hope we get more problems like that. That was an easy one, wasn't it? Yeah, that was a good one. All right. Part B, find the angle between them. To find the angle between them, I use this formula. U dot V equals length of U times the length of V times cosine theta. Well, the good news is I already know u dot v. What's u dot v? 1. I figured that out in part A. So it's 1 equals. How long is vector u? How long is vector u? How do I find the length of vector u? It's got a square root. Square root of x squared plus y squared. So that's 3 squared plus -1 squared. Times, how do I find the length of vector v? Square root of 1 squared plus 2 squared. Cosine theta. So 1 equals, this is square root of 10 times square root of 5 cosine theta. Cosine theta is 1 divided by square root of 50. And then I do cosine inverse. So the angle theta is 81.89 degrees, 87 degrees. Again, does that seem reasonable? Let's draw a little picture here. The vector 3, negative 1 would be right about here. There's 3, negative 1. And 1, 2 would be like this. Does it seem believable that that angle between those two vectors is almost 90 degrees? 81.87? Certainly looks it. So that's a believable answer. All right. Part C. Find the component of u in the direction of v. All right, so we have a little rule here. The component of u in the direction of v is the length of u times cosine of theta. So, the component of u in the direction of v is the length of u. What was the length of u? Square root of 10 times cosine of theta. How much is cosine of theta? Well, theta is 81.87. Cosine of theta is 1 over square root of 50. So if you plug 81.87 in, you'll get 1 over square root of 50. We don't need to figure that out again. We already got it. Cosine of theta is 1 over square root of 50. So it's square root of 10 over square root of 50, or 1 over the square root of 5, if you want to reduce.
So when the line is absolute value,
Correct. When we're dealing with vectors, this symbol that looks like absolute value stands for length. So again, does that look reasonable? If I take this vector, how long is it in that direction? This first vector, how long is it in that direction? Not very long, is it? I mean, if you come down, it's pretty short. But that's a pretty small number, so that's believable. All right. Projection of u in the direction of v. We use our formula. It's u dot v divided by length of v squared. We already know the top is 1 because we already figured out u dot v. U dot v is 1. The bottom we already figured out. So that's square root of 5 squared, which is 5. And then we multiply by vector v. So we multiply by 1 comma 2. So that's 1 over 5 times 1 comma 2. So how do I take a regular old number like 1 over 5 and multiply by a vector?
Oh, God.
It's easier than that.
1i plus 2j.
And then how do you multiply by 1/5?
1/5 I plus 2.
You just distribute. So I don't even need to write it using i's and j's. I can just take this 1/5 and distribute it. So it's 1/5 comma 2/5.
What would it be wrong?
It would not be wrong to use the j's and the i's. Just seems unusual to use the j's and the i's because we haven't used j's and i's anywhere else in this problem. But would it be wrong? Of course not. Not wrong at all. Questions on that one? You try problem 2. E. Oh, yeah. Tried to skip E. Crap. Resolve U into U1 plus U2, where U is parallel to vector V and U2 is perpendicular to vector V. All right. Well, the good news is we're halfway done. What it wants us to do is it wants us to take u, vector u, and write it as two vectors, u1 and u2. u1 has to be a vector that's parallel to vector v. We already have that vector. What's the vector that's in the direction of vector v but has something to do with u1? There's a name for that. It's called the projection. So u1, remember what the projection does? The projection gives us the vector in this direction that has the length, it's hard to describe. The length of this vector is the amount that this vector goes in that direction. Not very much. That's called the projection. The projection is the parallel vector that you need. So this vector is parallel to that vector, vector 1, 2. So u1 is always the projection. So u1 is the projection, which is 1/5, 2/5. That's the parallel vector. Plus the perpendicular vector. To get the perpendicular vector, to get u2, you take the original vector u, which is 3, -1, and you subtract this projection that you just figured out. That's the perpendicular vector. All right, so what this is getting at, why in the heck would you want to do that? Who cares? Now you see how good my artistic skills are. Let's say you had a van sitting on a ramp. That's a van of some sort, yeah. It could be a truck. Could be a truck too. It's whatever you want it to be. All right. So, for example, this ramp. Think of this as being like Cedar Street, and you're parking your car on Cedar Street. And what do you want to not happen? You don't want your car to roll down the hill, right? So your car has weight. So the vector for weight is going straight down in that direction. But what you really want to do is you want to know this vector and this vector. And these two vectors would be perpendicular. So you want to take this vector here, the weight vector of the van, and you want to split it into two perpendicular vectors. And this is really the important one, because what does this vector tell you? It tells you how much weight is going in that direction down the hill. So it tells you how strong your brakes have to be in order to keep that car from rolling down the hill. So that's what we're dealing with here. So this vector here would be the projection, and then this one would be the perpendicular one. And so that's the one you really want to know, because that's the one that tells you how to keep your car from rolling down the hill. Okay. Now, truthfully, we're not going to do a lot with that in this class, but that's why you might want to do this. Why would you want to split a vector into a parallel and a perpendicular? If you wanted to, I mean, you could do 3 minus 1/5, and you could do -1 minus 2/5 and simplify it. Be a nice answer. Not bad.